Morning. Let me help you with the EC calc because quite a few people are struggling. So this is what is currently on Mole, and this was an example calculation. This was to try and make it easier for you to understand. So this isn't always going to be the same because this was an example from last year, so things may have changed. You need to go through here and see if it's the same. So the brief says reinforcement, for example, is 260. That is still the same. And the density of steel, 7,800. So that's still the same. So I think people are struggling with how you work out this volume. Well, if the units of density, the units are kilograms per meter cubed. So you should know that density equals mass, effectively kilograms, and volume, meters cubed. So that's the formula to associate density, mass and volume. Should be from A levels and before. So you know the density. So you know the density and you know the mass, but you're questioning the volume. So you just rearrange that formula to give you the volume equals the mass divided by the density. The mass you've actually got is 260, so 260 here is the mass, which is the mass, the mass here, which then goes into that divider. And then if you go to the volume, if it was a meter cubed, so what proportion of a meter cubed is the density here is 7,800 here. So the density goes here and then goes there. So you end up with the answer being 3.3%. So 3.3% of a meter cubed would be steel. So therefore, if you've got 3.3% of steel, the difference would be concrete. So you just minus one from the other here to get 96%. Now, just so you know, in reality, if this is a column we're talking about, if you looked on a plan of a column, so you're looking down, these will be square columns, not eye sections. Then you'd have this square column, and you'd have some reinforcement, and the reinforcement would be a series of bars, which may be either one in each corner or maybe more bars, and then you'd end up with a very fine bar tying all these together around to make what they call a cage. So that's a plan view of what the column would look like. So putting that back into context, we're saying that 3.3% or 3.33% is steel, and the rest is concrete. And because this is a composite material, that's why we have to do this. So we can then say this is the density of concrete, so 97% of that gives you the density of that part of the meter cubed, and we know that the 260 from above gets added in, so this plus 260, and that gives you your density of your meter cubed. So you'll need that to calculate the mass of the structure. Now, we could have said the EC factor for this element, which is concrete, has got one value, and this has got another value, and just use those. So this 2328 grams per meter cubed times one figure, and 260 times another factor per meter cubed. What I'm trying to do is create a composite. So for this material, which is this here is both concrete and steel, give a combined factor. So if you look at your spreadsheet, some people are struggling to find G92 because this spreadsheet has been updated now. These change on a regular basis, and the first thing you go onto the spreadsheet, when you get the one I've given you, it says check this is update. And if you check on that and it's updated, then you need to go and use some new figures, because these things aren't just a fact. Hopefully those of you who are doing 173 can see how things change over time So if people produce more efficient ways of producing concrete, then the embodied carbon factor will change. So we're saying in this instance it was 0.149, and this was using this figure for the 32/40 megapascal reinforced concrete. If I go to the new sheet, so if I clicked on the link and got the new one, then I got this here. Now first of all, this is quite a big document. You have to scroll through all these different tabs to get to concrete. Click on concrete, and then you get a big spreadsheet giving you the figures. If you zoom in on this, it takes a while to catch up. Let me show you a screenshot I've got, because it takes so long to catch up with it being such a big file. If you use Excel, it's well worth doing. So I actually imported copy of this. So this is the screen you'll get to, and you can see these figures here: 0.138, 4050, 0.159, 3545, 0.149. So 138, 149, 159. Go back to the example calculation, and I've added these figures in here: 138, 149, 159. So use exactly the same theory, but you put in new numbers. And what you're working out is the embodied carbon factor for a composite material. So in this example, you'd got 346.8, which came from this calculation using the old figure, so that would reduce this time. And for the steel, that's using a tab here. Now if you look at the new tab, the new Excel spreadsheet, and see if this has changed, you'll find it hasn't, so this will be the same. But this sum here added up to 864, which went into this part to give a combined factor of 0.33. That now will have reduced. So what you need to do is to do that calculation, and this pro rata has also changed. And what I'm just saying there is, if you look at something and say, if you looked at the graph and said, if it's at 30, 40, 50 and 60, and you've got a figure here and a figure here and a figure here, and they're roughly in line, then you could extrapolate. And because these figures aren't too far out, I'm saying it looks like you can extrapolate. If this curve was going like this or was going like this, you may not do the same. So hopefully that's a just quick summary of what I'm expecting to do. You should end up with 6 figures. So you'll end up with, if you go to the brief, you've got piles, you've got slabs, and you've got just one calculation for each, because they're always the same concrete grade, always the same steel. And then you've got shear walls and columns, and there'll be 2, because there's 2 concrete grades in each of those.